Yeah. Okay, sir. Yeah. Uh, yeah. Good morning, my friends. I am Dr. Prasad Raju, Professor of Engineering from J into Canada. And very briefly about me, started my career about 25 years back. Did UG PG from Andhra University and PhD from GSA, Europe, Bangkok and other countries for academic and administrative purpose. Administration almost done the principal, registrar, director and now rector of the University of J&T Canada, and I have a number of awards, out of which Institute of Engineers Best Paper Award and also Best Teacher Award by the state government. And compared to all these things, the happiest, I thank Professor Srinivas Kumar Garu, Vice Chancellor of J&T Anandapur, and also Professor Ramangraju, Vice Chancellor of J&T Canada, for their encouragement and initiation, and also thank Professor Achinana and Professor Srinivaslu, DAP Anandapur and Faculty Development Canada, for giving the opportunity. And coming back the gate, it is not only for getting the PG admissions in superior institutions like NIT, IIT, etc., but also it is necessary and advantage for PhD admission also. Getting PhD admission without having a test, you can also attend interview. And not only that, based on the GATE score, some of the candidates are getting jobs also, direct jobs without any interview. These are the advantages. Hope you are all safe and secured against COVID-19. I also welcome not a difficult subject. It is quite easy provided you follow the concepts, fundamentals and derivations, problems, much easier. Slightly theory may be there, and you can score very good marks. And once again, the other issue is should be strong in fundamental units also. Fundamental units also. In this regard, I thank my research scholar, PG students, and also the colleagues who have encouraged me, and also PA for their help in preparing slides, etc. And some material also have taken from AS and fluid mechanics and hydronic materials by Mondel. I thank them for their permission and all these things. And coming back to the subject fluid mechanics, as all of you know, for the benefit of students, as it is online, I am going a little slow. The fluid mechanics is the branch of science, as you know, which deals with the fluids at rest as well as in motion. When you take up the fluids at rest, it is called fluid statics. The study of fluids at rest is fluid statics, and study of fluids in motion, there are two types. One is kinematics, other one is dynamics. Kinematics and dynamics. When you consider the study of fluids in motion, when pressure forces are not considered, so we have different forces are there. When pressure forces are not considered, we can consider that study as fluid kinematics. The other one is the study of fluids in motion, and also the pressure forces are considered. So it is called fluid dynamics. So basically fluid mechanics means we deal with fluid statics, that means fluids at rest, and fluid kinematics, that is study of fluid in motion. About fluid, just now I mentioned fluid mechanics, so it is covering fluid statics, In other words, fluids at rest, fluid kinematics, study of fluids in motion when pressure forces are not considered, and fluid dynamics, study of fluids in motion when pressure forces are considered. The other one is fluid. In simple words, you can say that fluid is a substance which is capable of flowing. A substance which is capable of flowing, in simple sentence, you can say that it is a fluid. For example, when shear force is applied, the fluid has a continuous deformation. It goes on moving as long as the force is applied. When shear force is applied, as the fluid is capable of flowing, it will have a continuous deformation or indefinite deformation as long as the force is applied. You can take fluid means it is maybe liquid or gas. Two are coming under fluid. Liquid means it is a fluid, possesses a definite volume. The volume is definite, so we can place it in a container, definite volume, and it is very difficult to compress under normal conditions. Difficult to compress under normal conditions. Gas is a fluid. Gas is also a fluid, no definite volume, but which is compressible. So basically, we have a liquid and gas. So for the gate examination, each and every definition, fundamental concepts are all very, very important. So the entire questions and the way you answer the gate examination, the doubt depends on your ability to understand the basic concepts and fundamentals there on the advanced topics. Liquid means it is also a fluid, but possesses a definite volume, but difficult to compress under normal conditions. Anything can be done under extraordinary conditions, but normal conditions it is difficult to compress. The other one is a gas, is also a fluid. Gas is also a fluid, which is compressible, has no definite volume. Basic difference. And a solid, as you know, solid has a finite deformation. As a whole, the solid as a whole it will move and it has a finite deformation. And for example, you take two types of fluids. One is ideal fluid. The other one is real fluid, ideal fluid and real fluid, ideal fluid and real fluid. So ideal fluid name itself is very clear. It is a theoretical fluid, which is not existing in nature, theoretical fluid. In other words, all the properties, fluid properties are neglected for ideal fluid, and whereas real fluid, it is also called practical fluid. In other words, it is available in nature. Practical fluid means it is available in nature. Ideal fluid is a theoretical fluid. In other words, ideal fluid means which has no viscosity, no surface tension, and incompressible. All the three are very important. And when you reach answering the gate solutions for gate questions, you will understand the importance of all these things. So ideal fluid, ABCD may give all the different answers. One option is no viscosity, no surface tension, and incompressible. All the three are important. And practical fluid, once again, you can expect that it should have a viscosity, all the properties, surface tension, and also compressible. That is practical or real fluid. And for example, when ideal fluid is set in motion, if you apply some shear force, and let us say the fluid is set in motion, allowed to move, and there will be no resistance offered in the opposite direction. Because it is a purely ideal fluid. It is all the properties are neglected. Keep on moving and there will not be any resistance in the opposite direction. In other words, when the fluid is set in motion, no resistance is offered by the ideal fluid. Example, air and water. For example, you take a practical fluid. When the practical fluid is set to motion and it is allowed to move by application of shear force, resistance is offered. We have viscosity and which opposes the forward movement of flow, and resistance is offered as it is a real fluid when it is set in motion. And similarly, solid and fluid. So solid has finite deformation, as you know from strength of materials. Both mechanical and civil students, you might have aware of solid mechanics or strength of materials. And when shear force is applied, solid has a finite deformation. Deformation is limited, and whereas the fluid has infinite deformation. That is the basic difference between solid and fluid. Solid and fluid. The other aspect is no slip condition. No slip condition. It is very, very important for objective time. What is no slip condition? I will go back to the next slide and come back again. So, for example, we see this sketch. And there are two parallel plates. There are two parallel plates. So, one is stationary plate. You see, the bottom plate is stationary. This plate is stationary, and the top plate is moving. So you see here, the plate is moving here, and the plate is stationary. This is stationary. And consider the fluid between two plates. Fluid motion between two parallel plates. These two plates are parallel. Plate, top plate and bottom plate are parallel. And we have a fluid here. Inside between two plates, we have a fluid. What are the observations? For example, we have viscosity. The fluid has viscosity property. It is a real fluid, natural fluid. And whatever the fluid which is in close contact with the stationary plate, the fluid in contact with the stationary plate, the fluid in contact with the stationary plate will have zero velocity. This is a stationary plate. The bottom one is a stationary plate, and the fluid is it is capable of flowing. What happens for the fluid at the bottom plate? So the fluid which is close to the stationary plate, the velocity of the stationary plate is zero. Stationary means the plate is not moving. The velocity of the stationary plate is zero. So the velocity of the fluid which is exactly on the bottom plate is zero. And on account of viscosity, the fluid adheres to the bottom plate. Adhesion, as you know, adhesion means it is attraction between molecule of liquid and molecule of solid. There is adhesion and also cohesion. Cohesion means it is intermolecular attraction. Attraction between molecule of liquid and molecule of liquid. Intermolecular attraction is cohesion. And whereas adhesion means it is attraction attraction between the solid and liquid. So because of adhesive property, because of the viscosity property, the fluid adheres to the bottom plate. In other words, you can say that the fluid velocity on the bottom plate is zero. Exactly, you can see the velocity distribution diagram also. Here it is zero. So you can say that no slip condition is the condition when there is no relative motion between the solid and the fluid. That is called no slip condition. So because the fluid adheres to the plate here, and as it is adhering to the plate here, the fluid has zero velocity, and this is also having, this stationary plate is also having zero velocity. So both plate and fluid both are not moving. So there is no relative motion. When there is no relative motion between stationary plate and the fluid on the stationary plate, we can say that it is no slip condition. No slip condition. Very important for objective, gate point of view. I'll come back to the viscosity. Yeah. So no slip condition when there is no relative motion between the stationary plate and the fluid which is close to the stationary plate, we can say that it is no slip condition. Then the fundamental properties of the fluid. In the fluid mechanics, the fundamental properties are very, very important. So often you will be getting all these properties in almost each and every part of your fluid mechanics subject. And in the fluid mechanics, we have a fluid dynamics, fluid statics, and flow through pipes, etc. Each and every chapter will be getting these fundamental properties. The student who is not aware of the fundamental properties, he will face difficulty in understanding the subsequent chapters. Very difficult, not difficult to, know the fundamentals or fundamental properties, but one issue here in fluid mechanics, particularly for civil mechanical students, you should have confidence in units also. What are the units for particular property? The unit conversion of one system of units to other system is also very, very important. For example, take mass density. Mass density very clear. Mass per volume, very clear. Mass per volume. Mass of the fluid in a given volume at 4 degrees centigrade normally for water. The mass density is 1000 kg mass. I will come back to you why it is mentioned. You can straight away write 1000 kg per meter cube. Why I am mentioning mass? Because it is. And similarly, if you see the properties of, so it is kg mass here. I'll come back to that again for discussion. And it is mass per volume. Volume is, as you know, it is meter cube. Volume is meter cube or 102 MSL. MSL means metric slag. Metric slag, this is meter cube. Correct that. This is meter cube. 102 MSL per meter cube. MSL is metric slag. Metric slag. I will come back to that. What is MSL? And also 1 gram per cc. 1 gram per cc and 1 MSL. 1 MSL is equal to kg force second square by meter. Why I am stressing this again and again is the students will be confused with the system of units, and viscosity unit is there. It is also more or less like this: kg force seconds by meter square. Square viscosity unit, but whereas here this is kg force second square by meter. I mean, it is small difference between mass density and viscosity units. So the students, some of the students may be a little confused with the system of units, as those units are almost more or less similarities. Or so in SA system, it is mass density for water is 4 degrees centigrade. In SA system, 1000 kg mass per meter cube, and MKS system, it is 102 metric slugs per meter cube. 12 minutes January. So 102 MSL per meter cube, metric slugs per meter cube, or 1 gram per cc in FE system. SI, MKS, all the systems are important, because in the problem you may be giving one in one unit, other in other unit, and 1 MSL, 1 metric slag is equal to kg force second square by meter. And for example, mass density is proportional to pressure and inversely proportional to temperature. So mass density depends on the molecular spacing. In other words, number of molecules in a given volume. For example, you take a temperature. With increase in temperature, what happens to mass or molecular spacing? So molecular spacing increases with temperature. Molecular spacing, suppose if you go on increasing temperature, what happens to molecules? So the molecular spacing increases. In other words, as the molecular spacing increases, and the number of molecules in a given volume will be less. So mass density is the number of molecules in a given volume of a fluid. So as molecular spacing increases with temperature, and there will be less number of molecules in a given volume. In other words, the mass density is inversely proportional to temperature. So as the temperature is more, the mass density decreases. As the temperature is less, mass density increases. Inversely proportional. The understanding is it depends on molecular spacing. So the molecular spacing again it depends on temperature. With more temperature, the molecular spacing increases. So the mass density is inversely proportional to temperature. More or less like this. And so we can apply more pressure to bring the molecules into closer. In other words, you can say that the molecular spacing decreases with pressure. You apply more pressure so that you can have more number of molecules in a given volume. And why I am stressing this is don't confuse with when you write your objective gate questions. So because he tries to confuse you, temperature increases, temperature decreases, pressure increases, decreases, something like that, ABCD. So you can always remember that the pressure is directly proportional to mass density. In other words, as molecular spacing decreases with pressure, in other words, you can pressurize more number of molecules in a given volume. In other words, the pressure increases with mass density increases with pressure. Mass density decreases with temperature. This is more or less same explanation for fundamental properties. So one matrix line is equal to kg force second square by meter. Kg force second square by meter. And the specific weight of water, only difference between specific weight and mass density is the weight per volume and it is mass per volume. Weight per volume and mass per volume. Only difference. And in SI system, it is 9810 Newton per meter cube or 1000 kg force per meter cube or 981 dynes in CJ system. SI system, MK system and CJ system. This is also CJ system. The specific weight of water, for example, you see here in MK system is 1000 kg force per meter cube. Similarly, the mass density here, you can see that in SI system 1000 kg mass per meter cube. Some of the students are there confusing with 1000 kg per meter cube. Sometimes you may mention only 1000 kg per meter cube. Only it may be specific weight. Specific weight of water is 1000 kg per meter cube means it is the unit given in MK system. For example, 1000 kg per meter cube mass density means it is the unit given in SI system. Because I know, from the last 25 years, I am in this profession. The students, mostly they are, confusing with kg mass and kg force. So that's why I am stressing here. So the mass density in SI system, SI, is 1000 kg per meter cube actually. I included mass here, 1000 kg mass per meter cube as it is a mass unit in SI system. And the 1000 kg force per meter cube is the unit in MK system for specific weight of water, kg force. That's why I included force here for weight. So 1000 kg force per meter cube is unit in MK system for specific weight, and 1000 kg mass per meter cube is unit in SI system for mass density. Please be clear, and it is very, very necessary for you, particularly in writing gate objective questions. And the other one is relation between mass density and specific, both are same. Specific density both are same. And some of the relations try to remember on your own. Need not start deriving the small relations. So you can easily derive with the 2 to 3 steps, but try to remember. So you are writing the answers in the gate examination also depends on your memory. Perfection. Memory is also important. Try to memorize the formula. You cannot have time for deriving the equations while writing the gate examinations. The other is specific density. In other words, mass density. Specific mass density rho is equal to specific weight by acceleration to gravity. G, as you know, in the gravity is 9.81 meters per second square. 9.81 meters per second square. So specific density is equal to specific weight by gravity. So in other words, normally specific density is represented as rho. Density is represented as rho, and the specific weight is the small w by small g. So rho is equal to w by g. It is very, very important relation, very small relation. The other one is specific volume. Specific volume. So specific volume is reciprocal of mass density or specific weight. Gas problems, gas flows, you can take, and also reciprocal of mass density. Either that means the specific volume is equal to either 1 by mass density or 1 by specific weight. 1 by mass density, or reciprocal means 1 by mass density or 1 by rho or 1 by small w. So 1 by mass density or 1 by specific weight. And what is the unit of specific volume? So because it is 1 by rho, it is meter cube by kg. So as you know the unit of mass density, so mass density unit is kg mass per meter cube. It is meter cube by kg mass, reverse. Again specific weight is Newton per meter cube in SI system. And the unit of specific volume is meter cube by Newton. Just a reciprocal of mass density and specific weight is specific volume. Don't confuse about the units. The mass density unit in a mass density is 1 by rho and specific weight is 1 by small w. So that means meter cube by so meter cube by kg force and meter cube by Newton also. So volume of the fluid by specific weight or 1 by rho, units are same. So meter cube either I can take meter cube by Newton or meter cube by kg. Similarly, specific gravity of fluid. Specific gravity of fluid. So specific gravity of fluid is as you know, it is a ratio of specific weight of fluid by specific weight of water. Ratio of relative density. Sometimes it is also called the ratio of relative densities. Ratio of relative densities. So ratio of specific weight of fluid by specific weight of water. Ratio of specific weight of fluid by specific weight of water. What is the specific gravity of water? It is equal to 1. Specific weight of water is equal to 1. And what is the specific gravity of water is equal to 1. Specific gravity of fluid is ratio of specific weight of fluid by specific weight of water. If you want to find out specific gravity of water, it is specific weight of water by specific weight of water. It is equal to 1. Specific gravity is equal to 1. And then what is the specific gravity of mercury? So specific gravity of mercury is equal to 13.6. Kerosene maybe 0.8, 0.9, less than the weight of water, specific weight of water. So specific gravity of oil or kerosene, etc. It may be 0.8 or 0.9. And specific gravity of the soil, for example, take it is 2.61, 2.61. And sometimes the students are also giving unit for specific gravity. Specific gravity has no unit. Specific gravity has no unit at all. Specific gravity has no unit at all. Urgent, generate urgent. So specific gravity of fluid has no unit. Ratio of specific weight of fluid by specific weight of water, same units. So specific gravity has no unit. Sometimes even in examination objective I am giving a unit of specific gravity something. But specific gravity has no unit. Yes. So the other is viscosity. Very important point. Very important point. Viscosity. Fundamental, very important property, viscosity. So what exactly mean by viscosity? Viscosity is a property. Viscosity is the property of the fluid by virtue of which fluid offers resistance to deformation. viscosity is the property of the fluid by virtue of, it is the property of the fluid by virtue of which fluid offers resistance to deformation. Whatever the resistance offered by the fluid, it is only because of viscosity. Important property. And you have a Newton's equation of viscosity. We'll come back to that. Newton's equation of viscosity is a famous equation, and based on that we can solve many number of problems. The shear stress is shear force by area. Shear stress is shear force by area, which is equal to dynamic viscosity into this is the change of velocity and this is the distance, rate of deformation. Dynamic velocity, viscosity, dynamic viscosity into du by dy. Mu into d by dy, Newton's equation, tau is the shear stress. So shear stress is shear force by area, and the dynamic viscosity, and du by dy, Newton's equation of viscosity. Let us come to this figure. We have two parallel plates in continuation of our earlier discussion. So this is a stationary plate and this is a moving plate. Stationary plate and this is moving plate. And this is having zero velocity and this is having the velocity equal to, let us say, v. The plate is moving with a velocity v. The plate is the plate has zero velocity here and the plate is having the velocity equal to v. For example, consider there is a fluid inside. So there is a fluid inside between two parallel plates. The Newton's equation of viscosity is valid only when the plates two are parallel. There are two important assumptions while arriving Newton's equation of viscosity. One assumption is the two plates must be parallel. The second assumption is the space between two plates must be very small. Very small. Why it should be small? As the distance between two plates is small, that's why we are assuming as a linear variation. Linear is a straight line variation, not a curvature variation, it is a straight line variation. And this is the top plate here, which is moving with a velocity v. And before going to that, the fluid velocity here, we have zero here. As you know, the fluid which is close to the bottom plate adheres to the bottom plate, and the fluid which is close to the top plate, it adheres to the top plate. The fluid attaches here with zero velocity, and the fluid joins here with velocity equal to velocity of the top plate. In other words, the fluid velocity of the top plate is the velocity of the top plate. The fluid velocity here is equal to velocity of the top plate, and the fluid velocity here is the velocity of the bottom plate. It is zero here and v here, and this is a linear variation. And the velocity varies from 0 to capital U. The velocity of the fluid varies from minimum 0 here, 0 to capital V. And this plate is moving with a velocity v with a shear force F here. So the plate is moving with a velocity v with shear force F here. So the shear stress, what is shear stress? Shear stress is force by area. So A is the area of cross section of the top plate. A is the area of cross section of the top plate. So the shear stress is equal to force by area. And as a shear, suppose if there is increase in shear force, what happens to velocity? So with increase in shear force, the velocity also increases. So because the plate is moving with force, and the velocity also depends on the application of shear force on the top plate. So the velocity of the top plate depends on the shear force applied. In other words, the force is proportional to the velocity. With more the force, more the velocity of the fluid here. With less the force, less the velocity of the fluid here. I am coming out how the relation, how Newton's equation of viscosity is coming out with the simple concepts here. Now we have the stress here. So stress is a force by area. The shear stress is a force by area. So tau is the shear stress here, and this shear stress is proportional to the rate of deformation here. So in other words, it is equal to du by dy. So what is du? Du is the change of velocity, relative velocity. So du means relative velocity. What is du here? The velocity of the top plate minus velocity of the bottom plate. So the velocity of the top plate is v and the velocity of the bottom plate is 0. So the change of velocity is v minus 0. In other words, v. So more generative form, more mathematical form, I am taking v is equal to du. So du is there. This velocity change happens in a distance of y. So the velocity, distance between two plates is y. So the shear stress is proportional to du by dy. So du is the relative velocity. Du is the velocity of the top plate minus velocity of the bottom plate, and dy is the distance from the two plates here. So in other words, the shear stress is proportional to du by dy. We have number of questions, objective questions on this particular topic, viscosity. So in other words, we can say that the shear stress is equal to proportional to d by dy. Then when shear stress is proportional to d by dy, and when you want to make equal, shear stress is equal to some proportionality constant multiplied by d by dy. This is the concept here. Shear stress is proportional to d by dy, and when it is made equal, so this dynamic viscosity is the constant multiplied by d by dy. This is Newton's equation of viscosity. Here two aspects are important. One is the shear stress is proportional to d by dy, and proportionality constant is dynamic viscosity. I will come to the viscosity in a short time. And Newton's equation of viscosity, there are two assumptions here. One is the two plates are parallel, should be parallel. The second one is the spacing between the two plates must be minimum. Otherwise, you cannot expect a linear variation. Those two are assumptions. Based on the assumptions, you can derive Newton's equation of viscosity. So now what is dynamic viscosity? So dynamic viscosity is also called coefficient of viscosity, same name. Maybe thinking that coefficient of viscosity may be different and dynamic viscosity may be different, or viscosity may be different. Coefficient of viscosity or dynamic viscosity or viscosity, all the three are same. And sometimes deliberately may confuse you viscosity. Viscosity means always it is dynamic viscosity, or quotient of viscosity or dynamic viscosity or viscosity, all the three are same. Then next step is units. Units are very important in fluid mechanics, particularly the conversion from one system to other system. So you can get the viscosity is equal to tau by d by dy, shear stress by rate of deformation. And the unit is in SI system 1 Newton seconds by meter square. Newton second whole by means whole by Newton seconds by meter square. What is the conversion between Newton to kg? 1 by 9.81. So this is 1 by 9.81. So 1 Newton second per meter square is equal to 1 by 9.81 kg seconds per meter square. And this is 1 by 9.81. So 1 Newton second per meter square is equal to 0.102 kg second per meter square is equal to 10 poise. 10 poise. Poise is a common word, common unit normally given the examination. It is the system of unit in CS system for viscosity. 10 poise. And this important relation between one system to other system is having a lot of importance and advantage while doing problems or while understanding anything. Normally we will confuse in a system of units. So it will be very clear. Sometimes we will be giving in centipoise. Centipoise is 1 by 100 poise. 1 by 100 poise. And 10 poise is equal to 10 dynes seconds per centimeter square. Dynes. Force unit in CS system. Poise means 1 poise. Sometimes you may be asking what is poise. So poise is dynes seconds by centimeter square. So 1 Newton second per meter square is equal to 0.102 kg second per meter square is equal to 10 poise. Every problem you will be giving a quotient of viscosity in poise and other in other system. So try to convert this into SI or MK system. Depends on the objective type question, and it is required for you to remember this. 1 centipoise is 100 by 100 poise. The other one is kinematic viscosity. So simple viscosity means obviously it is required for you to take dynamic viscosity. So kinematic viscosity means it is also having relation between quotient of viscosity or dynamic viscosity with simple mass density. But the units are different. Kinematic viscosity unit is different. Sorry for the interruption. So there was some problem. Yeah. So we are discussing. Viscosity, and the other issue we are discussing is kinematic viscosity. So kinematic viscosity, as you know, it is equivalent to dynamic viscosity by mass density. Dynamic viscosity by mass density, and the unit is Stokes. So normally the unit of poise for dynamic viscosity and unit of Stokes for kinematic viscosity, both are very important. Normally the problem in giving something in Stokes, something in poise. Instead of giving all the kg force per second square, all these things, you will be giving in Stokes. So one Stoke is equal to square centimeters per second. In one system of unit, other system it is meter square per second. But Stokes is equal to centimeter square per second, and this is the other system is meter square per second. So the kinematic viscosity is also very, very important. The relation between the kinematic viscosity and the dynamic viscosity relation is important. It is nu and this is mu. So nu is equal to mu by rho, and units are very, very important. So the other one is try to remember this: the gases, for gases viscosity is proportional to temperature. Gases, as you know, fluid means you have gas and liquid. So viscosity proportional to temperature for gases, and liquid viscosity inversely proportional to temperature. Gases viscosity proportional to please remember this: gases viscosity proportional to temperature, and liquids it is inversely proportional to temperature. And we have different types of fluid: Newtonian fluid, and non-Newtonian fluid. So what is Newtonian fluid and what is non-Newtonian fluid? So Newtonian fluid name itself is very clear that when it obeys Newton's equation of viscosity is called Newtonian fluid. Newton's equation of viscosity is tau is equal to mu into du by dy. Tau is the shear stress, mu is dynamic viscosity, and d by dy is the rate of deformation. So when it obeys Newton's equation of viscosity, it is called Newtonian fluid. When it doesn't obey Newton's equation of viscosity, it is called non-Newtonian fluid. So Newtonian fluid, non-Newtonian fluid, again object important object type question. So we have a linear way. When it obeys Newton's equation of viscosity means the variation between the stress and deformation, rate of shear deformation is linear. When some fluid is obeying Newton's equation of viscosity means there is a relation between stress and rate of deformation is linear. There is a linear variation between stress and rate of deformation for Newtonian fluid. And non-Newtonian fluid means when the fluid doesn't obey. When it doesn't obey Newton's equation of viscosity, it is non-Newtonian fluid. Yeah. So this is one picture that shows different types of fluids. On one side it is stress, shear stress, and this is rate of deformation. So tau versus dV by dy. And this is, see here, this is Newtonian fluid. So Newtonian fluid is a fluid which has a linear variation between tau and dV by dy. So the Newton's equation of viscosity is tau is equal to mu into dV by dy. Tau is equal to mu into dV by dy. Tau is proportional to dV by dy. So when there is a linear variation between stress and the rate of deformation, then you can say that it is Newtonian fluid and it is obeying Newton's equation of viscosity. The other one is a non-Newtonian fluid. So non-Newtonian fluid is a fluid which doesn't obey Newton's equation of viscosity. That exhibits here. There is a non-linear variation. Non-linear variation. Non-linear variation. And you see here, this is a plastic, this is thixotropy, and this is ideal. So ideal fluid, as you know, earlier discussion, it has no surface tension, no viscosity, all these things here. So that means whatever the stress here, if you see here, even when the stress is zero, and this is representing ideal fluid, when all the properties are neglected, and they have continuous deformation, there is no resistance offered in the opposite direction, which is representing ideal fluid, and this is elastic solid. The deformation is zero, and this is elastic solid, and the stress is zero. This is ideal fluid, important for object type. A plastic substance. So the plastic substance, it starts after only certain yield stress. So this is yield stress here. Some yield stress here, and deformation, if you see here, the deformation starts after certain yield stress. This is a plastic substance. Again, if you see here, this is having a linear variation. That means the deformation starts after certain yield stress, and you have a linear variation between stress and rate of deformation. That is a plastic substance. And the other one is thixotropy. Thixotropy substance is also starts the deformation after certain yield stress. But stress is a non-linear variation with deformation. So when there is a non-linear variation, in other words, thixotropy substance is a non-Newtonian fluid for which the deformation starts after certain yield stress. Plastic substance is a Newtonian fluid, or obeys Newton's equation of viscosity, a Newtonian fluid, but which starts deformation after certain yield stress. So this is about types of fluids. You have some questions on types of fluids quite often in GATE examinations. And the study of non-Newtonian fluid is also called rheology. Study of non-Newtonian fluid. We have Newtonian and non-Newtonian fluid. Sometimes maybe mentioning what is rheology. Rheology means study of non-Newtonian fluid. Non-Newtonian fluid is a fluid which doesn't obey Newton's equation of viscosity, and there is a non-linear variation between stress and rate of deformation, and this is rheology. And thixotropy, plastic, and ideal, just I have mentioned in the figure itself. The other one is compressible and incompressible fluids. Compressibility and incompressible fluids. So compressibility means it is a measure of change of volume. Compressibility means it is measure of change of volume with the application of pressure. So when the material is subject to pressure, what happens to volume? So that is called compressibility behavior. So when you are applying a pressure to the fluid, how it changes? So measure of change of volume when it is subject to pressure. And for example, quantitatively you can express this as inverse of bulk modulus. You see here, it is proportional to 1 by K. Bulk modulus is K. It is proportional to inverse of bulk modulus. In other words, you can say that when you apply pressure, measure the change of volume with reference to original volume. So that is compressibility. So proportional to 1 by K bulk modulus, which is equal to K is equal to minus dP by dV by V. What is dP here? Change of pressure. So for example, take a cylinder in which a fluid is there and a piston. Piston cylinder arrangement, general arrangement, not a complicated arrangement. We have a piston and cylinder. Piston cylinder. So the pressure applied through the piston is, let us say, P1 initial, and the original volume is V1. So take a case, there is a cylinder of fluid and a piston is there. We can apply pressure through piston and the original volume is V1. Cylinder, original volume of the fluid is V1 and we have a piston, and through piston the initial pressure is P1. In other words, initial pressure is P1 on the fluid and the volume of the fluid is V1. And now you decrease the piston and apply pressure by moving the piston downwards in the cylinder. Now the pressure is increased from P1 to P2. Pressure is increased from P1 to P2, and the volume V1 will be reduced to V2. So when there is an increase in pressure, what happens? The volume decreases. So the pressure change is P2 minus P1 and the volume change is V2 minus V1. The pressure is increased from P1 to P2 by moving piston downwards in the cylinder, which is consisting of a fluid, and the volume initially V1, it is reduced to V2. Then what is dP by dV by V? It is also sometimes giving the exam papers. So dP means P2 minus P1 and dV means V2 minus V1, and this is V1. So P2 minus P1 by V2 minus V1 by V1. V1 is the original volume. Then why negative sign is introduced for the bulk modulus? Because the reason is P2 minus P1 is positive value. So we are increasing the pressure. So that is positive value. And V2 minus V1. So V1 is more than V2. So V1 is the initial volume and V2 is the final volume. Because of the pressure, the volume is reduced here. So V2 minus V1 is negative. So V2 minus V1 is negative and V1. So as dV is negative, to give positive value to K, negative sign is introduced there. So this dV is P2 minus P1 and this is V2 minus V1. V2 minus V1 is negative. So here negative is there and here negative is there. To give positive value to the K, negative sign is introduced here. So whatever the value will be getting is only positive value, not the negative value here. So this dV, which is V2 minus V1, is a negative value, and negative will be positive, and finally a bulk modulus is a positive value. So that's why a negative sign is introduced in the bulk modulus. So that is compressibility. Compressibility is inverse of bulk modulus, and bulk modulus is equal to change of pressure by change of volume to the original volume. Simple fundamental equation. Simple problems just will take up here. First problem. So mu is equal to, you see here, mu is equal to 1.5 y minus y to the power of 3 by 2. He has given the velocity here. Find out shear stress at y is equal to 9 centimeters. He has given viscosity is equal to 8 points. Simple problem, very simple problem. He has asked to find out. Shear stress. He has asked to find out shear stress. He has asked to find out shear stress. And what is the equation? We have Newton's equation of viscosity. Tau is equal to mu means viscosity into dE by dy. So dU by dy. So you can take a differentiation here. So we have a relation between u and y. We have a relation between u and y. So you can have a differentiation. So dU by dy. So then what is dU by dy here? So dU by dy is 1.5. dU by dy is 1.5 here, and this is equal to 3 by 2 into y minus 3 by 2 minus 1. So dU by dy is equal to 1.5 minus 3 by 2 y to the power of 1 by 2. So find out dU by dy. Find out dU by dy. So dU by dy differentiation of y is 1.5 here, and 3 by 2 into y, 3 by 2 minus 1 is 1 by 2. So 1.5 minus 3 by 2, y is equal to 1 by 2. So that is d by dy. And he has given y 9 centimeters here. So you can take y in meters. So 9 centimeters you can take in meters, 0.09, and find out the d by dy value. So d by dy value is 1.5 minus 3 by 2, and here the value is 9 centimeters, you can convert into meters, 0.09 to the power of 1 by 2. So d by dy, when you substitute y is equal to 0.09 meters is equal to 1.05. So you can find out d by dy, simple differentiation, and substitute this value here. And viscosity is 8 points. Now the question is, this is in CJ system. The 8 points is in CJ system. So you need to have, you need to convert that CJ system into either MKS or SS system. So the relation, as you know, 1 Newton seconds by meter square is equal to 0.102 or 1 by 9.81 kg/4 seconds per meter square is equal to 10 points. So convert viscosity, dynamic viscosity means it is dynamic viscosity. Don't confuse with the kinematic viscosity. If it is kinematic viscosity, the unit will be in strokes here. It is only dynamic viscosity. Dynamic viscosity unit is points or Newton seconds per meter square or kg/4 per second square meter square. So don't confuse this viscosity as kinematic viscosity. Kinematic viscosity will be either in strokes or centimeter square per second or meter square per second. Strokes or centistroke, that is different. This is the dynamic viscosity, is 8 points. So you can convert this in MK system. So 1 kg/4, 1 by 9.81 kg/4 seconds per meter square is equal to 10 points. Then viscosity is equal to 8 by 98.1. So viscosity is equal to 8 by 98.1. So 8 by 98.1 is viscosity in kg/4 seconds by meter square. So 8 by 98.1 is equal to 0.0815. 0.0815. So 0.0815 is kg/4 seconds by meter square, and d by dy is 1.05. So now tau is equal to mu into d by dy. So mu, we have a 0.0805 into d by dy is 1.05. So the answer is 0.085. 0.085 shear stress. So 0.08 shear stress is equal to mu into d by dy. So that's the value. You can easily find out. So mu value you can find out by 8 by 98.1, and d by dy is you can define differentiation and substitute the value. You can easily find out the shear stress. Shear stress is equal to mu into d by dy. So which is equal to 0.085. So that is the value here. Second problem. Find out the kinematic viscosity when dynamic viscosity is 8 points. Simple problem. So dynamic viscosity is 8 points here. Dynamic viscosity is 8 points here. And the conversion again. So if you want to convert the points in MK system, that divided by 98.1. So 8 by 98.1, 8 divided by 98.1. So that is 0.0815. 0.0815. So that is mu in kg/4 seconds by meter square. And kinematic viscosity is equal to mu by rho. Mu is 8 by 98.1, 0.0815. So that divided by mass density in MK system. So what is the, it is for water. So what is the value of mass density for water at 4 degrees centigrade in MK system? That is 102 MSL per meter cube. 102 MSL per meter cube. So mu by rho. So the value of mu is 0.0815 So that divided by 0.0815, so that divided by 102. So that is a 0.0079 meters square per second. Very simple problem, but only thing is convert the system of units, one system to other system. So 8 points you have converted to MK system. So MK system 80 by 8 by 98.1, that is kg 4 seconds per meter square. And the kinematic viscosity is equal to dynamic viscosity by mass density. So dynamic viscosity it is 8 by 98.1 and mass density in MK system is 102 MSL per meter cube. So we'll be getting kinematic viscosity meter square per second. That is a simple answer. So the third problem is, so 1 liter of crude oil weighs 0.96 kg force, 0.96 kg force. Find out the specific weight and mass density. 1 liter of crude oil weighs 0.96 kg force. Find out specific weight and mass density. What is 1 liter? So 1 liter means it is 1000 cc, 1000 centimeter cube. 1 liter of volume, which is equal to 1000 cc, 1000 centimeter cube. So which is also equal to 1000 into 10 power minus 6 meter cube. In other words, 1 liter is equal to 1 into 10 power minus 3 meter cube. Hear me, 1 liter is equal to 1000 cc and 1 cc is equal to 10 power minus 6 meter cube. So finally 1 liter is equal to 1 into 10 power minus 3 meter cube. So now the volume is 1 into 10 power minus 3 meter cube and weight is 0.96 kg force. Then what is the specific weight here? Specific weight is equal to weight by volume. So weight is equal to 0.96 kg force and volume is equal to one in 10 power minus 3. Then what is specific weight? Specific weight is equal to 960. So the volume is equal to 1 into 10 power minus 3 and the weight is equal to 0.96 kg force. So weight is equal to, specific weight is equal to weight by volume. So 0.96 by 10 power minus 3, that is the volume. So 960 kg force per meter cube, that is specific weight. And what is mass density? We have a specific weight value. And how will you find out mass density? So mass density is equal to specific weight by acceleration due to gravity. Specific weight by acceleration due to gravity. So that is 960 by 98.1. 9.81. 960 by acceleration due to gravity. Acceleration due to gravity is 9.81. So that is equal to mass density is equal to 97.85. Mass density is equal to 97.85 MSL per meter cube. And one small information. So tomorrow I have the Honorable Chief Minister is addressing through video conference for Vice Chancellors, Registrars and Rectors. So as a Rector of the University, I need to attend tomorrow's session, video session right from 10:30 to 5:30 here. So with the permission of all my student friends, I would like to take the class from 8:30 to 10:30. Sorry for the inconvenience. From the day after tomorrow onwards, it is normal as is. Between 10:30 and 12:30, I will be taking fluid mechanics from day after tomorrow. That is 28th onwards. The time is same, 10:30 to 12:30. In view of tomorrow's the Honorable CM video conference to the Vice Chancellors, Rectors and Registrars, I need to attend, required to attend from 10:30 to 5:30. That's why tomorrow online session with the permission, I already requested the organizers, the Vice Chancellors and the coordinators. And with maybe slightly inconvenience, but please bear with me. I try to slept early. And so that we can start the session at 8:30. From 8:30 to 10:30 only tomorrow, and after tomorrow it is normal. Yeah, again. And the problem here, the last problem, find out the viscosity when, because these are all simple problems, that's why I'm explaining simple steps, 1 or 2 steps, that's why I have not taken a slide here. Simple problems, find out the viscosity when shear stress is this value and d by dy this value. So if we have a shear stress, the equation is tau, Newton's equation of viscosity, tau is equal to mu into d by dy, tau is equal to mu into d by dy. So he has given shear stress, tau is equal to 0.025 and d by dy is 0.3. So then mu is equal to tau by d by dy, tau by d by dy. So that is 0.025, 0.025 by 0.25 divided by 0.3. So that is 0.083. So mu is equal to 0.083 kg/4 seconds per meter square. These are all very simple problems. Only thing in the problems you will be confusing where I can understand here only between systems of one system to other system. Here you need to convert the poise into MK system or SI system. Need to convert effectively, and here the conversion is 98.1 to convert into MK system. And here you need to convert effectively. Here this is also poise. And this is 1 liter of crude oil. You need to convert the volume in meter cube. 1 liter is 1000 cc, and 1000 cc is equal to 1000 to 10 power 6 minus 6 meter cube. The slight conversion from one system to another system. The equations are different here. Same equations. So here tau is equal to mu into d by dy. Newton's equation of viscosity. Here kinematic viscosity mu by rho. And here fundamental specific weight is weight by volume, and mass density is mass by volume. The fundamental relations. And again, this is Newton's equation of viscosity. All these four are very, very simple, provided you know Newton's equation of viscosity and conversion of one system of units to other system of units. And the other one is bulk density. The other problem here is he has given the pressure change. So this is bulk density K. As you know, K is equal to change of pressure by change of volume to original volume, change of pressure by here. So the bulk modulus is equal to change of pressure by change of volume to the original volume, change of pressure by change of volume to the original volume. We take a small problem, right? So the pressure change is 40 kg per centimeter square. The pressure change is 40 kg per centimeter square. And volume decreases by 0.2%. When there is increase in pressure, obviously volume decreases. And what is the value of K? So K is equal to change of pressure 40 by volume decrease by 0.2%. He has given dV by V. So this percentage means he has given dV by V. That means it is 0.2 by 100. So that means it is 40. So 40 is the change of pressure. So 40 divided by 0.2, because it is in percentage, so you need to take in 100. So 40 by 0.2 by 100. So we are getting 800 kg force per square centimeter. So the answer is 800 kg force per square centimeters, because so this is 40. The change of pressure is 40 by dV by V. dV by V is 0.2, not in percentage. 0.2 by 100. 0.2 by 100. So this value is equivalent to 800 kg force per meter square. So this is okay. So the equation is 40. So 40 divided by 0.2 into 100. 20,000. Okay, not 800, 20,000. So this is the answer here. 40 by 0.2 by 100. 40 here, 0.2 by 100. Again, for gases, the bulk modulus is proportional to temperature. So the bulk modulus here is proportional to temperature and also proportional to pressure for gases. So the bulk modulus is directly proportional to temperature, directly proportional to pressure for gases, and liquids. So because gas and liquids are also fluids here, for gases the bulk modulus is proportional to temperature, proportional to pressure, and liquids the bulk modulus is proportional to pressure and inversely proportional to temperature. Please remember here, and normally you will confuse in late questions. So for liquids the bulk modulus is proportional to pressure and inversely proportional to temperature. For gases, proportional to temperature and proportional to pressure. So the other aspect is surface tension. What is surface tension? So another important aspect, what is surface tension? So in simple words, you can say that the surface tension is force required. Simple words. It is the unit is Newton per meter. The unit is Newton per meter. It is force required to maintain unit length of film in equilibrium. Whatever the force required at the surface to maintain that in equilibrium is called surface tension. For example, you take this figure, intermolecular forces near a liquid surface. Intermolecular forces near a liquid surface. One at interior, one in the liquid interior. So one at the exactly at the surface. What are the observations here? So this is the molecule in the, this is all liquid here. So this is the free liquid surface. This line is the free liquid surface. What is free liquid surface? Free liquid surface is the surface. If it is, it will be exposed to atmosphere. So whenever the surface is exposed to atmosphere, it is called free liquid surface, and the pressure on free liquid surface is atmosphere pressure. So atmosphere air always exerts a normal pressure on free liquid surface, and the pressure on free liquid surface is obviously atmospheric pressure or barometric pressure. As the pressure is measured with reference to barometer, it is called barometric pressure. And so the pressure here is atmospheric pressure, and this is called free liquid surface. As it is exposed to atmosphere, as there is no other pressure other than atmospheric pressure, it is called free liquid surface. And this is all fluid. Above that is top liquid surface, free liquid surface or top liquid surface here. And consider one liquid molecule at A in the liquid interior. So in the entire liquid body, you take one liquid molecule at A. One liquid molecule at A. Then this all in equilibrium. Equilibrium means this is at rest. So the water, this all we are discussing static equilibrium. The fluid is at rest. Fluid statics, fluid at rest. So this fluid is at rest. In other words, the molecule is in equilibrium. The liquid molecule is in equilibrium. And how it is in, it will be in equilibrium. The reason here is, if you take a molecule at A, and we have number of molecules surrounded by the molecule A, this is the molecule at A, and around that we have a number of molecules surrounded, and because of the cohesion, please remember, the surface tension is only due to cohesion. The surface tension is only due to cohesion. Cohesion means intermolecular attraction between molecule of liquid and molecule of surface. So because of cohesion, what happens here? So this is a molecule at A, and we have molecules around that, and we have here we have a molecule here. There is a attraction between molecule and molecule, and this is surrounded by all the water molecules around that, and which is equally attracted to all the sides. So the molecule at A is in equilibrium because of equal attraction between all the other molecules which are around that molecule A. So molecule A is in equilibrium because it is equally attracted by all the other molecules which are around that molecule at A. So the molecule A is in static equilibrium. Molecule A is in rest condition because it is attracted towards all the sides in view of the cohesion. So that's why the molecule at A, the water molecule in the liquid interior, obviously in equilibrium because of the cohesion force, and as each and every molecule is attracted on all the sides by other molecules around that, it is equilibrium. Then what happens when you take a molecule at surface? So molecule at surface, we see here, this is the molecule at surface, and here we have molecules on all the sides. Here we have molecules on all the sides except on the top. So there is no molecule on the top here. We have water molecules on all the sides. So consider the molecule here. and we have molecules on all the sides except on the top. Then what suppose there should be a net down, because the upward pressure you see here, the upward pressure is very small here. So we have the forces, drag forces on all the sides, and we have it is attracted towards all the molecules around this molecule except on the top. So we have no molecules on the top here, no molecules on the top here. Then what happens here? There should be supposed to be a net downward force on the molecules at the surface. And the molecules exactly at the interface, air, this is the air here, this is the water here. The molecules at the surface exactly, which are at the surface, and these molecules, there should be a net downward force on the molecules which are existing at the surface, because there is no upward force which is counteracting that. But the reason is these are also in equilibrium. The molecules at the surface are also equilibrium, even though there is a net downward force on the molecule at surface, but these are also equilibrium. The reason is surface tension. So the molecule at B, molecule at A is obviously equilibrium, because we have number of molecules on all around the A, but whereas B, we have molecules on all the sides except on the top side. But that is also an equilibrium, that is also a static equilibrium, because the reason here is surface tension. That's why I am mentioning the surface tension is a force required to maintain unit length of film in equilibrium exactly at the surface, air-water interface. So surface tension is the force required to maintain unit length of film in equilibrium exactly at the interface here. So the unit is force per meter length. Force per meter length is Newton per meter. Again, the unit of surface tension is also important. So unit of surface tension is force per unit length, and surface tension is force per unit length. And the surface tension, try to remember three expressions for surface tension. For water droplet, P is equal to P, the pressure. P is equal to 4 times the surface tension whole divided by D. D is the diameter. So D is the diameter, and P is the pressure inside, and this is surface tension. P is equal to 4 sigma. Normally we giving surface tension as sigma. P 4 sigma by D. You remember the equations, not necessarily the expressions here. Hollow bubble. Hollow bubble is a soap bubble. Sometimes it is also called soap bubble. You have two faces here. So that's why this is P is equal to 8 sigma by D. So 8 into sigma by D. So 8 is the value, constant value, and sigma is the surface tension, and then divided by D. D is the diameter, and liquid jet. We have dimensions here. So liquid jet is 2 sigma by D. So try to remember these three equations. Normally, at least one problem on surface tension in every gate examination. So P is equal to 4 sigma by D, and hollow bubble is 8 sigma by D, and liquid jet is 2 sigma by D. So where D represents the diameter and P represents the pressure. The other aspect is capillarity. So the capillarity is the phenomenon of rise and fall. So the capillarity means the phenomenon of rise and fall. You can say it is a capillarity. So for example, see here, there is a rise here. For see here, there is a fall. This is the liquid surface here. If you dip a capillary tube, so here we have dipped this capillary tube in the water. And this is the free liquid surface, and there is a rise of water here. And this edge is called a capillary rise. And whereas suppose if you place this in mercury, so this is the water here, and this is the mercury here. And if you place this capillary tube in mercury, what happens here? There is a depression. So mercury specific gravity is 13.6, and water specific gravity is 1. Water specific gravity is 1, and mercury specific gravity is 13.6. So here, when you place a capillary tube in water, there is a capillary rise. When you place a capillary rise in mercury, which is strong in cohesion, there is a depression. So the phenomenon of capillary rise in depression is called capillarity. Capillarity is the phenomenon of capillary rise in depression, and this capillarity is due to both cohesion and adhesion. Normally asking in the objective type questions, surface tension is due to cohesion and capillarity is due to both cohesion and adhesion. Cohesion is intermolecular attraction, adhesion is attraction between liquid molecule and solid molecule of solid. Very, very important. Surface tension is due to cohesion and capillarity is due to both cohesion and adhesion. Now I take a simple example on that. Take a solid surface, take a solid and place a water bubble on a solid surface. Take a solid surface, any solid surface, and place a water bubble on the surface. What happens? It wets the surface. You cannot get the water bubble as it is in the same form. The water wets the surface. It is a solid surface. It is a solid surface, and place a water bubble on the solid surface. What happens? It wets the surface. It wets the surface. The water will not be in the same form when you place that water bubble on the solid surface. It wets the surface. What is the reason for that? The reason is the adhesive force is more than cohesive force. What is adhesive force here? What is cohesive force here? The adhesive force is the force of attraction, a force between the molecule of liquid and molecule of solid, which is dominating, which is more than cohesive. Cohesive force is intermolecular attraction between the water molecule and water. So the cohesive force is between intermolecular attraction, molecule of liquid and molecule of liquid, and the cohesive force is between the molecule of liquid and molecule of surface, molecule of solid. So as the adhesive force is dominating over cohesive force, in other words, as adhesive force is more than cohesive force, because of that it wets the surface. That's why when the capillary tube dipped in water, there will be obviously a capillary rise, not the depression. Why only a capillary rise in water? Why not in mercury? Simple example of that. When a water bubble placed on the solid surface, it wets the surface because of the more adhesive force compared to cohesive force. That is the capillary rise and capillary depression. For example, you place a capillary tube in the mercury, there is a depression. What could be the reason of that? For example, if you take a mercury bubble and place it on the solid surface, what happens? And it doesn't wet the surface, and the mercury is in the form of same bubble as you placed earlier, and we can have a mercury bubble on the wet surface as it is, even with time, even with a period of time. What could be the reason there? So the reason is the cohesive force is more than adhesive force. So cohesive force is the force of attraction between molecule of liquid and molecule of liquid, and whereas adhesion is between solid and liquid. So the mercury will have more cohesion. When you place mercury bubble on the solid surface, because of more cohesive force compared to adhesive force, this the mercury bubble will be in the same form. It remains in the same form. That way, there the adhesive forces are more dominating in mercury, and the cohesive forces are more dominating in mercury, adhesive forces are more dominating in water. There is entirely different behavior. Adhesive forces are more for water when it is placed on the solid, and cohesive forces are more for mercury when you place it on a solid. So because of this entirely different behavior, when you place a capillary tube in in water, there is a rise. When you place a capillary tube in mercury, there is a depression. So the phenomenon of capillary rise and depression is called capillarity. A small equation. Normally, how we are going to find out a equation for capillary rise? For example, see here, And when you do not place any capital tube, this should be a liquid surface level. When you place a capital tube, there is a rise of water level. Then how will you place the value of H here? How will you place the value of H here? So you can equate the downward force and upward force. You can have a downward force here and upward force here. The upward force is due to surface tension. Due to surface tension here. So if you see here, this is sigma. Sigma is surface tension which is acting at an angle of theta. This is the pressure here inside. Theta is the contact angle between glass and water. Theta is the contact angle between glass and water. And this sigma is the surface tension. And this P is the pressure. And this is a 2r, r is the radius, and d is the diameter here. Then how will you get the expression for capital I? Simple, try to remember as far as possible the equations, otherwise I can give a small steps here for arriving at the value of H in a simple way. And this is the downward force here, and upward force is due to surface tension. And what is the downward force? Downward force is due to the weight of the fluid, which is above free liquid surface up to here. So we have a downward force or downward weight. This is due to the weight of the fluid, which is above free liquid surface up to the height of H here. Then how will you find out the weight of the fluid which is above free liquid surface up to H here? And this W is equal to pi d squared by 4. What is the volume of the glass tube here? What is the volume here? So the cross-section area is capital A. Let us say the cross-section area is capital A, which is equal to either pi r square or pi d squared by 4. And the volume of water above this up to here is area into height of rise. Area of water above free liquid surface into height of rise. So the volume here is equal to pi r square into H. And what is the weight here? So specific weight is equal to weight by volume. So weight is equal to specific weight into volume. So volume is pi r square H, and specific weight of the water is known here. So the downward force is equal to weight, which is equal to small w, and small w is specific weight into volume. Specific weight of water is known, and the volume is pi r square into H. And then what is the upward force here? That is the downward force. What is the upward force here? So if you see here, the upward force acts over the perimeter. The contact of the surface tension is force per meter length. So meter acts over the circumference, not over the circumference. Circumference is pi d or 2 pi r. So this is the downward is the specific weight multiplied by pi d squared by 4 into H, the volume, and this sigma is acting over the circumference. So sigma into pi d. So sigma into pi d is circumference, but it is acting at an angle of theta here. And you need to convert, this is inclined direction, you need to resolve this in the vertical direction. So sigma into pi d, and what is the angle here? So the opposite side is horizontal, and so the other side, adjacent side is sine theta. Opposite is sine and adjacent is cos theta. So this is the upward force is sigma. Resolve this in vertical direction. So sigma cos theta into pi d is circumference. So the upward force is sigma into pi d cos theta, and the downward force is w into pi d squared by H. So after simplification, it is H is equal to 4 sigma cos theta by w d. So you can as well remember the equation or try to get into 3 steps, but the time is important. You can acquire downward and upward. Sometimes in the he's also giving a 2 marks or 5 marks question. Sometimes maybe asking a derivation also. You need to derive also in 2 to 3 minutes. If it is a 1 mark objective type, you need to remember the equation and also remember the procedure of getting the equation, which is also required for 2 marks and 5 marks questions. So both are important. So that's why here upward force is equal to downward force. Downward force is due to weight of water in this area and upward force due to surface tension. So finally H is equal to 4 sigma cos theta by WT. Take a small example here on surface tension. On surface tension, so he has given the surface tension here. Surface tension here at 20 degrees centigrade is equal to 0.0073. That is surface tension, and pressure he has given 0.0015 kg per centimeter square. To convert into one system, it is meters here and it is centimeters here. Convert either in meters or centimeters, both are same. Convert both into one systems here. So we have a P in kg per meter square and surface tension value in kg per meter. So now we have a surface tension value and we have also pressure value here. It has also find out diameter of the water. Let us say it has not given, but water. Then what should be the water for diameter of the water droplet? We have three equations for surface tension. One is P is equal to 4 sigma by D, so that is for water, and P is equal to 8 sigma by D, that is for soap bubble, and P is equal to 2 sigma by D for liquid gel. So this is for the water. So water means you need to use the equation 4 sigma by D. P is equal to 4 sigma by D. P is 4 P value is there. Convert in kg per meter square. 4 sigma. 4 into sigma. Sigma value is there. 4 into 0.73. So P value is known and sigma value is known. Known diameter is not known. So P is equal to 4 sigma by D. 4 into 0.073. And the P value is there, you can find out the diameter. Simple problem, it is based on equation. P is equal to 4 sigma by D. For example, you see here for water in capillarity, adhesive force is more than cohesive force, and mercury cohesive force is more than adhesive force. Please remember, the surface tension is due to cohesion and capillarity is due to both cohesion and adhesion. Once again, I am repeating, surface tension is only due to cohesion and capillarity is due to both cohesion and adhesion. And the contact angle, if you see the contact angle between glass and water, the contact angle between glass and water, for example, if you see here, this is the contact angle between glass and water is 0. Between glass and water is 0, whereas between glass and mercury it is around 130 degrees. So contact angle between glass and water is 0. If it is 0, what is cos 0? Cos 0 is 1. And contact angle for mercury and glass is 130. So you can find out the capital rise for water and capital depression for mercury. Sometimes he is giving water and also mercury. Sometimes he may be asking capital depression. Sometimes he may be asking capital rise. So the equation is H is equal to 4 sigma cos theta by W1D. So 4 sigma is the surface tension, theta is the angle of contact. Theta by the angle of contact, it is 0 for glass and water. So cos 0 is 1. And 4 sigma by W1D. Sometimes we have water and sometimes we have oil or anything like that. For example, the specific weight of water is 1000 kg force per meter cube, and if the specific gravity is 0.9, the specific weight of 0.9 fluid is equal to 900. So it is very simple because the specific gravity of fluid is specific weight of the fluid by specific weight of water. Specific weight of water is known. If you want to find out the specific weight of fluid, specific weight of water multiplied by specific gravity. For example, if the specific gravity of the fluid is 0.9, if the specific gravity of the fluid is 0.9, what is the specific weight of fluid? So specific gravity of the fluid is 0.9, which is equal to specific weight of fluid by specific weight of water. So specific weight of fluid is equal to specific gravity is 0.9 and specific weight of water is 1000 kg per meter cube. So 0.9 into 1000, it will be 900. So if it is for the fluid or specific gravity 0.9, this becomes 900 kg force per meter cube. If it is a water, it is 1000 kg force per meter cube. In SI system, it is 9810, 9.81 G. So in SI system, it is 9810 Newton per meter cube. In MK system, it is 1000 kg force per meter cube. You need to, know the values of the specific rate of water in different system of units. Now the problem here is value of, you wanted to find out the capital rise. Find out the diameter, you want to find out the diameter. So he has given the capital rise, that means the value of H is he has given, and he has given the value of sigma. Sigma in the surface tension is known here, this is known here, and this is known here, 0.5 is known here, and this is known here, and cos 0, theta is 0 here, and cos 0 is 1, and this is for water. If he has not given anything, you can take water here, this is 1000, and he has asked to find out D here. So convert, this is again, see here, this is in mm, convert in meter, so 0.5 10 power minus 3. So convert this value in, so again it is required for you to convert one system of units to other system. So this is in mm and this is in meter, kg per meter. So this sigma is 4 into 0.00725 and D is not known, and this is 1000 kg force per meter cube, and H value you need to convert. Sometimes the students are taking in 0.5, but it should be 0.5 into 10 power minus 3 in meter, because both are in meters here. So you need to convert in meters, and from that you can find out D value here. So these are general problems, just I am mentioning. I am explaining the method, how you solve this problem, and the actual problems, great problems, I have solutions afterwards. I have a theory and problem, and I can give it to you. But meanwhile, what I am telling you is because I have given the procedure for evaluating the problems, at least earlier 5 problems, this is one problem, 6 problems, try on it on own, and try to get solutions in the correct way. I have tried to give answers for all the 6 problems tomorrow, exact values. For all the 6 problems which were already discussed with you. And tomorrow I will give solutions, direct answer, because I have expanded the procedure for finding out the problem solution. So try to work out these problems with the procedure given by me, and try to have the solution with you, and tomorrow I will give the solution, straight away answer for all the 6 which I have given. The other one is vapor pressure and vacuum pressure. Very close similarity between vapor pressure and vacuum pressure. So normally the students are mostly confusing is vapor pressure and vacuum pressure. What exactly mean by vapor pressure and what exactly mean by vacuum pressure? Vacuum means obviously you can say that it is a negative pressure. Negative. Vacuum means creating some vacuum. Vacuum means negative. Negative pressure. What exactly mean by negative pressure? So negative pressure means the pressure less than atmospheric pressure. What is atmospheric pressure? Atmospheric pressure is, take any free liquid surface, as it is exposed to atmosphere, the atmosphere air which exerts a normal pressure, for example, you see here, this is not for surface tension, this is a free liquid surface, the atmosphere air which exerts a normal pressure on free liquid surface, so the pressure created by atmosphere air on the free liquid surface is atmospheric pressure. And as the pressure is measured with the help of barometer, we can say it is also barometric pressure. So barometric pressure is 1.03 kg force per square centimeters. Atmospheric pressure is different. And if the pressure is less than atmospheric pressure, if the pressure is less than atmospheric pressure, you can say it is vacuum pressure. Any pressure less than atmospheric pressure is vacuum pressure. Any pressure less than atmospheric pressure is vacuum pressure. Atmospheric pressure is 1.03 kg force per square centimeters. You can also get in meters of water, meters of mm of mercury. We'll come to that in the next chapter. But vacuum means negative pressure, which is less than atmosphere. It is also called vacuum is negative pressure, also called suction pressure. We have three names for that: vacuum pressure, negative pressure, suction pressure, negative gauge pressure, less than atmosphere. All the five related to same. More or less, vacuum means less than atmosphere pressure and negative pressure. So negative pressure is entirely different. Vapor pressure is different. What is vapor pressure? What is vapor pressure? So vapor pressure is different. So vapor pressure is the name itself is very clear that the pressure created by vapor when it vaporizes. When it vaporizes. So that you can say it is vapor pressure. Then, for example, you take a container. You take a container in which there is a fluid. Inside the container there is a fluid, and the top of the container is open. Take a container, and it is having fluid inside the container, and the top of the container is open. Top of the container is open. Then what happens? In other words, the top of the water in the container is exposed to atmosphere. A fluid is there inside the container for which the top of the surface is open. Top is open. Like a mug, let us say we have a water in the mug, the top is open. Then what happens here? So the top of the surface is not as it is open. What happens here? So the top of the surface is open. Top of the surface is open. What happens here? So as the top of the liquid surface is open in a container, as it is exposed to atmosphere, what happens here? Whatever the vapor bubbles, whatever the bubbles there will be continuous escaping of vapor bubbles into the atmosphere. Because the top is open here, it is exposed to atmosphere. And atmosphere, there is atmospheric pressure on the liquid surface. As the top of the liquid surface is open in a container, there will be escaping of molecules from the top surface into the atmosphere. That is one issue. For example, at the same situation, when the vapor molecules are escaping into the atmosphere as the top surface is open in a container consisting of a fluid, then what happens when the container is closed? We have a fluid inside the container, but it is closed. There is a difference between the top of the container and the liquid surface which is there in the container. There is a gap between the top of the container which is closed now and the free liquid surface which is slightly below the top of the container. There is a clear gap between the top of the fluid inside the container and the top of the container. Then what happens here? Still there is a escaping of molecules. So there is escaping of molecules and there is no way for the molecules to go out as the top of the container is closed. The molecules, in other words, there is a fluid inside a container and the top of the surface is closed and there is a gap between the top of the container and the fluid inside the container. There is a gap. So because of that gap, what happens here is the water which is there in the fluid, which is the vapor which is there inside, there is a continuous escaping of vapor molecules into the atmosphere, but which is prevented by the top surface which is closed now. Then what happens here? Then there will be accumulation of vapor bubbles. There is accumulation of vapor bubbles above the free liquid surface and below the top of the container in the same container. There will be accumulation of bubbles. Then these bubbles which create a partial pressure on the liquid surface, and that is called vapor pressure. Vapor pressure is the pressure created by the accumulation of vapor bubbles when the top of the surface is closed. That is called vapor pressure. And you can also say that vapor pressure is the pressure at which the liquid is converted into vapor. Vapor pressure is the pressure at which the liquid is converted into vapor. Vapor pressure is the pressure at which the liquid is converted into vapor. So why I am stressing this again is the students are more or less they are confusing vapor and vacuum. Vapor is entirely different. Vapor itself is very clear that it is due to the vapor formation of vapor bubbles. Vacuum itself is a negative. Vacuum is negative. Negative space. Suction, negative. Negative pressure, negative gas pressure, negative atmosphere. Suction, vacuum, both are same. Both are entirely different. So you'll be getting this discussion in GATE online questions. But slightly one or two objective questions only today I will discuss, and try to remember whatever the theory we have discussed today. And I have given some 6 problems. I have discussed the solution, how to go about it, how to do the problems. Try to work out those problems with the help of the procedure I have given to you. And we'll try to discuss the solutions straight away tomorrow, right at 8:30. First, the 6 problem solutions tomorrow. Straight away answer for you. And in addition to that, we'll have a series of objective questions in this on this chapter. We have some 30 questions, objective questions. But for those for answering those objective questions, this discussion of theory, this discussion is very much necessary, very much important for you to answer confidently the questions which we are going to discuss tomorrow. In addition to those questions, I have taken the help of my student friends for getting the questions which were given in ACE coaching center, and there is one of the standard books are there, and fluid mechanics admission by objective questions, gate questions by some test books, and my colleague and PA and scholars, they have helped me, and they have given good support to me in the preparation of PPT and objective questions, all these things here. And I have gate questions also, which were given in earlier examinations, a series of gate questions, maybe 10 or 20 on the same chapter. So we'll try to discuss each and every gate question and whatever the problem solution we have. I will straight away try to have a PPT on solution also, so that you can have a immediate discussion on that, and you can get a solution immediately with complete understanding. But in addition to that, I will try to give some problems for you, and I will try to give a procedure for solving the problem, and try to do on it our own in our house, and try to come back to me on the next day, so that gives an experience for solving the problem, and this is the exposure for solutions. So those two must be there. I am thinking of doing that. Anyway, tomorrow we'll be starting the session at 8:30 with the permission of the organizers and vice chancellors, because of the importance of meeting. Supposed to attend as a rector to the CM sir video conference from 10:30 to 1:30 tomorrow, again 2:30 to 5:30, completely engaged. I thought of taking the evening, but almost done at the evening. So morning preferably I will be ready by 8:15 here. I request the organizers to give a link so that I will connect immediately right at the point of time 8:30. Straight away we will start the solutions and objective questions tomorrow for this chapter, and we will start the second chapter also. But this fundamental chapter is very, very important for you to understand. That's why I have spent enough time on this chapter. Not only for solving the problems in this chapter, but also for getting the derivations much easier if you have the concept of this chapter. So again, thank you very much for the organizers and also my student friends, the students who are hearing me, and you can give me the feedback. I have given the questions also. We have one mail ID in the first slide I have given to you. The mail ID is, this is rectal is official mail, but you write gvrproj@gmail.com. This is the slide is there. Please note down gvrproj@gmail.com. So that I will try to answer those questions immediately or in the next class. Whatever the question, anyway, you are giving the feedback through Google format directly to the organizers. They will also send it to me the information, and also you can directly make a copy to me so that I will straight away, suppose if the question is very simple, I will straight away answer to that particular person, and that the problem is solved and he will be happy with the answer. But if the question is really serious and which is required for all the students to know this particular answer, then I will discuss that answer in the online class. Okay. Tomorrow I will be hearing my voice at 8:30. Thank you all. Hope I am audible and hope I am clear. Anyway, give me your feedback so that if there is any shortcoming, definitely I will try to improve on that. A lot of experience, 25-30 years teaching, and good interest and attitude to talk to the students, and I love to talk to the students. And I'm sorry for the small interruption in between, a 5 minutes interruption. Even though we have operated immediately generated, there was a current problem, and there was some problem there in the power, and again we have rectified immediately, and absolutely no problem, and a small inconvenience in between is slightly extremely bear with us, and thank you student friends, and thank you organizer for giving me the opportunity, and again I will come back here tomorrow. Thank you.